What I'd like to do is sort of show you some of my intuitions about network visualization, some new ideas about network visualization, and some new tools for network visualization. Because as it tunes, and then help you sort of get a little bit of intuition about why we do it and where it comes from. So I'm going to go through the things relatively quickly, sort of, but in favor of being able to show you this in a demonstration. In the too long didn't read sort of version of this is very few visualizations are good out of the box. Computer science has spent a very long time coming up with pretty good graph drawing algorithms. But every graph drawing algorithm is a trade-off that is unlikely to be the trade-off you would have made to make the picture you want. There are on the horizon, excuse me, a handful of AI-trained visualization layouts, where they've done is they've taken visualizations that people like and trained the layout algorithm to generate networks that people like. So that's a very promising direction, but those tools are not ready for consumption yet. So at least in the meantime, I'll show you some things that you can do quickly that look reasonable, some things you can do quickly that look terrible, so please don't do those, and some things you can do that are going to take a little more time, and maybe a little bit on the horizon. Because this is lunchtime, don't be at all shy about interrupting me and asking questions or whatever. You should never be shy, but that's the plan. Again, the history of visualization in networks is really long, and quite frankly, for people like me, I think for many people, could someone pull that door shut just because I know I'm a loud mouth? People sort of got into this world because we like network visualizations. There's a certain beauty and attraction and something just like fascinating that all of this thing around us that we hadn't been able to see before, we can see. That's just like, there is something to that is really, I don't know, for me anyway, mesmerizing and capturing in a way that is just really, few things can do as well. As, picture's 1,000 words. Some of these pictures are well worth the words. This is one of the networks that started this whole thing, right? So this is from Moreno's Who Shall Survive, which if you don't have that book, you ought to grab it. He's a little nuts, but it's kind of a fun read. And to think that they're doing these kind of diagrams by hand in 1934, 1932, I forget which year it was, is kind of remarkable. And because I'm going to go through this example in detail later, this was one of the cabins of wayward youth. These were wayward girls that Moreno studied in the book. And his convention was that each node is a kid. Each relation is a nomination from one to the other. If it's reciprocated, there's a little bar across it. Otherwise, it's directional as we expect. Positive ties are in red and negative ties are in black. That's a little bit, sort of, our intuition is usually the opposite. But in contemporary days, it's sort of some fun conventions, right? So here you see that MT dislikes AC and AC likes MT, and they indicate that as a reciprocal tie, but of different colors, right? So it's kind of a fun it's a really interesting thing that's happening here, because what you see is the ethnographic kind of intuition that was built into doing community studies at the time got put into these kinds of diagrams. And what you see at the end is that there was a question about CM, for example, who everyone seems to dislike, and the only close friend CM has only one friend otherwise, right? So this little dyad out here is kind of left on the world by themselves, and that ends up being an important part of the story that Moreno tells. And so the thing to keep in mind here is that the layout algorithm they used was an RA with a pen, right? So it's like, there were a few tricks they had. They had some pegboards with rubber bands and things like this to sort of get a rough draft. But by and large, they were sort of sitting down with a ruler. And if you discovered halfway through that this guy was actually in the wrong spot or this person was in the wrong spot, you either had to redo the entire thing over again or live with it, right? And so there's a lot of that going on. And some of these, this is from a really nice book. It's in the bibliography of the slides, but this book is many, many pages, and these are households and visits between households. And so this was a prominent sort of woman in this community. She was the wife of the mayor, if I remember right, or something like that. I'm sure I'm going to forget. But this is a classic sort of image that you see a lot of times in these things. And it's another example of sort of the, I don't know, the Art Deco beauty that's built into this. But at the same time, this is sort of interesting fidelity to the underlying scientific data. Because what you don't recognize from this world is that all of the graphs across the different pages of this book are linked. So in this case, this tie comes out here. These 4 ties go to the prior page, and you can pull them in. So all these ties coming in are coming in from another page. So literally the entire network, if you could put it together, is out there, and they've just taken windows and sort of rearranged them and let you see it. And so it was a really, there was an intuition in the original work that this amount of work, right, to do something like this is worth it. And so why is it worth it, right? It's worth it because it's an in-depth investigation of what this world looks like and a chance to see it and identify patterns. And these patterns and who's connected to who, this was a way to make this visual. And it really was an ethnographic tool as much as it was a scientific visualization for quick communication. And there's lots of different ways to do this. Unfortunately, we went from those beautiful things that Lundberg and Steele and Moreno were producing to this. Right? So this is a published graph in somewhere, I don't remember where. I think I removed the names to protect the innocent, but or the guilty, as the case may be. But like, this is miserable. Right? It doesn't tick a beauty box. It doesn't tick an information box. It's just like, someone had to publish something in a hurry and they just left. If this is your diagram, I apologize, but there you go. Diagrams need to do something for the audience. And so one of the reasons I like these, kind of like this graph I showed earlier, is that it allows you to sort of think with a presenter. And that's how I typically use them, is to have that sort of model. But sort of the guiding feature behind visualizations, for me anyway, is that they have to build an intuition about some underlying social process that generates the network. They have to succinctly capture this high dimensionality that's there. They need to be worth the space, right? So the information content of the image needs to be worth the inspection. And they should be pretty, right? There's a certain element, we shouldn't forget the craft of data visualization. And there are times when that's worth the effort and exploration and so forth. But if you're going to take someone else's time to look at your picture or a page space in a journal, right, at the publication stage, it should be worth the space. And so if you're going to do that anyway, take the time to make it pretty. As a scientific standpoint, there needs to be data fidelity. So that's a necessary feature. So the graph has to reflect what's really in the data. And it needs to be replicable, to a first order. That's actually really difficult to do in a hard sense. I can talk about that a little bit as we go forward. Most of the features that we care about in the network are quantifiable. And so you're clarifying those within some kind of, usually a rank order, if not an actual cardinal value. And then again, it needs to be theory relevant. And so how do you do that? So you move from the thing the machine gives you to something you do to that output. And so the difference between these two is that this is what a visualization program called PAYAC, which I've used a lot and I like. It does a nice first order job. And I'm going to explain what this is and how it got here in a second. And our thinking we were doing a paper that on missing data, and we were comparing across a lot of different networks, and the things that mattered in those comparisons were differences in centrality and differences in clustering. And so we really wanted to sort of highlight in the output in the images a way that was, you could look at for a minute. And so we tried to pick a color scheme that was easy on the eyes and find a way to unpack a lot of these clusters while highlighting the centrality. So we used both color and size to get centrality, and a lot of hand jiggle. We wrote a little tool, a script to jiggle these, but essentially to jiggle them off top of each other. All right, so how do you get here? You get here usually by starting with a network layout algorithm and then futzing with it. And so what are network layout algorithms? So network layout algorithms are tools that computer science have built for us that let us quickly come up with a low-dimensional representation of these high-dimensional objects. And so there are a handful of them, and they fall into 3 basic categories. The first, and I'm going to talk about 2 and then sort of introduce the third along the way. So the main 2 are tree-based layouts or directional layouts and force or space-based layouts. So in a directional layout, really all this is that there's some inherent ordering or meaning to the y-axis. And so for hierarchy, this is exactly what you would want, right? So we have a root and the network goes down, and the hierarchy is the story. And the x-axis is really just there to uncross the edges. Whereas in a force-based layout, what you're trying to do is represent the social space that's otherwise unobserved, and so what you have is some feature like an edge link that you're trying to present in order to pull it together. Whereas if you end up with so tree-based layouts are good when your network is ordered. They're really bad when your network is not ordered, right? So the question here is that you want to figure out what kind of layout algorithm can generate a good outcome. For most of the things that we want to do in social network analysis, for health reasons, the force-based layout is probably the default. That's what you're going to use, and I'm going to just give you another example here in a second for how we do that. But they're usually sort of incomplete. The third base that I'm not going to talk about at all today, other than just to show you, are fixed coordinate layouts. So if your space is known, maps can be useful. Maps distort social reality. So you just need to know about there's a trade-off there. All right, so how do you get to these things? There's lots of things under the hood that I'm not going to go through, including all the stuff on dynamics. And I just want to take you through this original example again. And so what we wanted to do, and to sort of help you think about our thinking, which is that this was a really nice graph in the sense that it's pretty to look at, but it fails some of the other science things. It doesn't push out sort of an understanding that you might see. And so we wanted to figure out, well, how might we replicate this kind of a flavor, but generate more information for the audience? And so the way we did it is we tried a bunch of different things. And so we took the original layout, and it turns out that this layout has what we call a fit to the underlying social space that's pretty low. And so this fit is the correlation between the distance on the screen and the distance in the network. And so this has a low correlation, whereas almost by definition, a metric multiple dimensional scaling, MDS, is an optimization of the layout to maximize that correlation. So in this case, you get a really high correlation, but you lose the story about the negative ties with CM. A Fruchterman-Reingold is a sort of under the hood, a different kind of MDS, and it does a slightly better job because this node sort of pops out on its own, but that part of the story also gets lost, and there's some nodes on top of each other. So we said, well, how would we fix this? And so at first we thought, well, maybe we would try one layout foundation and layer other things on top of it. In homage to the hand-drawing things, we used a font that looks hand-drawn, but otherwise it's the same kind of idea. And so if this were the friendship network, we could say, and this is the dislike layer, maybe we can sort of layer them over in some way that is nice. It didn't work. That works terrible, right? So that's all right, back to the drawing board. And so we said, well, let's try if we can maybe instead really just focus on this story that we keep thinking about, which is what CM is doing. And so let's center this network on CM and then think about what the orbits around CM are. And so we did that by running a clustering algorithm, and we nicely fell out into these three groups and a few hangers on, and this little isolated dyad between the two. And so when we did that, then we realized that if we could highlight those groups, that each of these groups has a central story of their own that is also talked about in the book, and that gives you this micro or sort of meso level and this macro level simultaneously. And then we just layered over it a series of things that aids to help the reader see it. So these shadings on the other side are added ex post in hand, and the colorings were chosen in order to try to comport with the kind of things that Americans, at least, are used to, which is green is good and red is bad. And so we sort of went through with that kind of a set. So this is an example that I've gone through quickly just because I wanted to show you the thought process in generating these kinds of networks. If you're going to do them for for publication and for others' consumption as opposed to just your own sort of immediate day-to-day analysis sort of sets, you often do just like you do when you write a paper. So generating a network diagram is no different than writing a paragraph or writing a page. You rewrite. You have a first draft, you figure out what the story is, you rewrite, you edit, you go back and forth again, and it's this interrogative process of yourself and the data in order to generate what you want. And once you get something close, then you sort of hone in on the final set. Now this diagram, there is no machine that's going to produce this for you with a push of a button. And that's one of the things that I think that I like about visualization is it requires you as an analyst to jump back into your ethnographic roots of social network analysis, which is social network analysis is a qualitative, quantitative method. It is a tool largely that requires you to use judgment and apply that judgment in a theoretical way that is informative to the process. And so that's what we do there. So how do you get, so that you get from the post to the sec, you lose the sort of hand-drawn artisticness of the sort of clustering of the lines in funny ways and crosses over and bits like this. But I think that from a scientific standpoint, we gain something for that loss. Fair?
Sort of silly question, but do you remember what community detection algorithm you used?
This was Louvain, where we did a search over the parameter space, and I think it was in this case a pretty high parameter space because or a resolution parameter because the default out of the box. The problem with is that it wanted to put those in a cluster, whereas they don't actually belong in a cluster anywhere. So we had to use a clustering algorithm that we tuned high enough that we could essentially put each of these in their own cluster. So that's what we did there. All right. So how do you do this? So the way you do this is, assuming you're all working in R, is you find a starting layout algorithm from R. Is this the right one? Yes, here we go. And if you look in the Slack page, I again have a little shiny app that we're developing for doing network layouts. And so the way it works is, again, you have these files that you can load, and the IdeaNet software will do part of this as well. This is just sort of a pushed up version of the IdeaNet visualizations tool. And so the data processing thing lets you pull in a network. You can either upload one that you already have or one of our preloaded ones. I wanted to show you first a very simple network, which is a 4 regular grid, and because that's a good way to understand how these visualization tools work. So we start with this, and we do some things we can figure out in terms of how we color it, although that'll make more sense in a minute. But I wanted you to just get a sense of what the different layout algorithms do. And so we say compute the layout and render the visualization. And so Kamada Kawai is an algorithm where it's trying to treat each space as it optimizes the uniformity of edge length. So any two edges that are weighted the same, they try to keep them the same distance so that every node that has a tie around it will have the same radius is the idea. And so this is what you expect to see, right? So in this case, let's rotate that a little. There we are. And so what you expect to see here is that a grid should look like a grid, right? So so it does a nice job of that. And all of your space-based layouts will do something like this. Of course, the orientation will be wrong, but some of them do a better job than others because they have different sort of underlying machinery. And so the Fruchterman Rheingold, which is the other most common one that we run, and if we compute the layout on that, you'll see in that case it failed partway through, and so the grid is folded over on itself in 2D space. And so we could try to compute the layout again, and we got it there. Instead, if we were to do another smart one, would be something like multidimensional scaling, which is an underlying space dimension reduction tool, compute the layout. And there you see, for some reason, what it's effectively trying to do is deal with these edge issues. And so the process of the edge is these nodes in the middle are closer to some of these other nodes than are these edges at the corner, and those kinds of spaces get moved in there. Some of these tools don't work as well as they might for this kind of a network. So this is also a space-based layout, but it's optimized for very large graphs, and it does a terrible job of this one, right? So out of the box, you'd think, well, this is a fancy one of the newer computer science sort of layout algorithms, and it's designed for really big things. A small network to a powerful program should be an easy problem. Turns out the shortcuts that it takes to solve big networks are going to make your network look terrible, right? So don't use that. And so these are on the tool. Again, it's in Slack. You can play with this all you want and have a chance to look at it. We put them here for historical reasons. This is the easiest layout you can do. It's useless. I'm not sure why you would ever use it, but it's there if you want it. Now let's go back and pull a real network that we might have heard about. So this is the Karate Club again. We'll process the data. I'm saying treat it as directed, but all of the preloaded networks are undirected graphs, so it's not going to show up anything there. The way this tool works is that we render the visualization, or sorry, you first compute the layout, and then you render the visualization. And I get rid of the circle layout. And let's just start with Fruchterman Rheingold. Compute the layout, render the visualization. So in this case, I have a uniform node size. That's probably not what we want. Just so I can zoom it in a little bit, I'm going to rotate it some so we can see it in like that. Edge coloring here makes sense. It's just shaded and thickness by the strength of the tie. This is a dynamic layout, so you can click and drag. And the one thing that I think that you're always going to need to get from the simple layouts to a final one is the ability to move things by hand, because you're always going to need to adjust things. It's just part of the, if you want it to look good, especially if there's a story you want to tell. The rule is adjust sensibly. Like, don't be stupid, right? So if you're moving something here and you think that this node's in the wrong spot and it could look better, that's fine. But you'll notice in this case that the story of the karate club is that this thing was split into two. So let me save the layout again so that my nodes don't move. I did it anyway. So let's run to the visualization. So I rotate this again. So in this case, right, if this node is kind of in the wrong spot, it would be better, it would sort of tell my story better if I put this node over here, right? That's lying, right? And so I say be really reticent to make a story that says, let's just make this thing look as separated as I possibly can. That's true, but if you haven't told people that you've gone in and futzed with the network, they're going to assume that this is an actual standard force-directed layout, and that the colors there should have been more like this. So you just need to be a little bit smart about how you do these kinds of features. Now once you have anything in the neighborhood, then we can start thinking about sort of the aesthetics of this process. And most of the time you're not going to want the IDs. Those tend to be pretty useless. So we get rid of those. And oftentimes, visually, you're going to want to size by something that is sensible in your setting. And usually that's something like degree. You'll see what happens when I do this by base degree. Why is that? Let's render the visualization. There we go. Base degree by itself isn't working so well, so let's make it a little bit smaller. Does that help? Render the visualization a little bit. Make it even smaller. So if I really wanted to keep it at the base level of degree, the stars are just so much bigger than everyone else that they're hard to see. So often what you'll do is do log degree, and then re-render that way, and just multiply that a little bit. Render again. And you can see how this works, right? It takes a little bit of back and forth to do it, but you get a chance to get to where you're at. Now in this case, those things are still, because they're now so big, they're overlapping. It makes sense to separating them a little bit. I don't consider that cheating, right? You're clarifying, you're making sense of what's there, and you're not changing essentially the rank order of where things are too much, but you're making it possible for people in a small graph like this to trace the edges and not misconstrue that an edge going under a node is an edge to that node. And that's the reason to do that. Please.
Say that, like, with plotting up the MDS layout kind of violates since the spatial integration matters based on.
Yeah, so if you're doing an MDS layout and you report an MDS layout, that the purpose of an MDS is data reduction, and those dimensions mean something. And so then futzing with it, if as a starting point, that's fine. But as and then just say, I started with an MDS and then adjusted for clarity. I have no problem with that. But if you say, this is an MDS plot without the adjusted for clarity, then it's just a little misleading. That's all. Now, there's a lot of things that you can do that people, I think, I say this word force-directed and you don't know it, but you can do, there are sort of fun things that R lets you do. I'm going to show you this because it's what the hell. There's a physics sort of simulation, which is another word for these force-directed layouts are a spring embedder layout. And the logic here is that each tie is a spring pulling us together, and there are invisible springs pushing nodes that aren't connected apart. And so you can play with that spring system, which that's kind of fun, right? So if this is the network of your department and you have someone you don't like very much, you can sort of try to drag them off. So there's lots of things like that you can do. In practice, I've found that these kinds of dynamics things, they have a natural sort of cooling schedule, so they always stop wiggling at some point, and they don't then be very pretty. So I tend to not do that and instead go back to the non-physics one. There are sometimes regions that you might want to enable something like shadows, for example, just to provide a little bit of depth in something like this. I don't know, maybe it helps, maybe it doesn't, but that's part of the idea. And so the thinking here is with this tool, and we're in the process of expanding this tool, but I wanted to put it here for you, and the code is on the website. And the beauty of it is that this is using this tool. Let's go down to the right code here. Oh, it's a thunderstorm out there. The tool that it's using under the hood is Viz Network. And so there's an entire sort of package of these tools. And the only reason to throw it into a Shiny app is that that's where you can get in there and move it around by hand. It's just harder to do that in other places. We're also going to expand this out for the rest because we're building Shiny apps anyway. But in open code, if you want to play with a what I think is probably the best production quality graphics tool for networks in R, this is high on my list. Otherwise, I think that the other thing that we've done with this is that we've generated this in such a way that you can write the layout out to your environment, and then you now have a data set in your set. I forgot what I saved it as now. Let's just stop this. Oh, here we go. It should be up here. I'm just not seeing it. Well, I'll find it for you later. It's supposed to be, anyway, what you get is a simple rectangular data set of all of the coordinates and sizes and so forth, so you can export it to any graphics feature you want to play with or otherwise work with it in that set. So these are fun. The final thing I just wanted to show you, because it's sort of the newest thing that people are doing, I believe, is everyone always asks me this, which is, well, why don't we use 3D? And it turns out that 3D has sort of, for a long time, 3D has been just hard to see on a two-dimensional screen. Our perception doesn't do it. And so there's this whole new group of people who are trying to use virtual reality to do 3D networks. So you can immerse yourself in the network itself. And Quan Liu, who's a co-author of Bob Ferris's, has a nice tool for this. Wayne Baker has a new tool for doing this. And I'm not going to show you the whole video. Oh, don't make me do this. Well, maybe I won't, because it's not on here. Do I have it local? So this is to give you a sense, I'm going to zoom through it, of how these things work. And so you're actually in the network, sort of moving around with them.
Users to expect intra-community connectivity.
And I'm going to shut them off because I want to talk, I don't want to listen. And so the beauty is that you can get in there and actually treat this as a physical object in virtual space and zoom into it, dig around it, point things, highlight different kinds of nodes if you want. This is the neural network of a worm, so it's not the kind of thing we'd be particularly interested in. But it does have some nice opportunities. They have some new edge bundling tools that they add to it to find clusters and so forth. So it has promise. Wayne Baker's tool is the same thing for dynamic networks with a little less clever edge bundling. I don't know if it'll be useful or not. It's probably fun unless you're epileptic, in which case then it might give you a seizure. But my favorite sort of way to deal with 3D, which people are doing now, is 3D printing your network. This is the one reason I might buy a 3D printer, because I have been playing with a certain set of networks in AdHealth my entire career, and I would love to just have a desk toy of it, for example. So I don't know that this is particularly useful from a publication or whatever standpoint, but if you're as an exploration tool to actually see it in physical space is kind of cool. So again, I couldn't find the actual software for doing this, but to visualize networks as sculptures, I think would be actually much nicer, because most of the layout problems with network visualization are because they are trying to put an n-dimensional object in a 2D space, and it rarely fits well. So this is kind of cute and fun. All right, I've already taken. I'm at the edge of where Scott's supposed to be, so happy to take questions on this. Either now or at Stump the Chumps where we switch over. But there you go, please.